So last time, what we had, so we started talking about mechanical vibrations. And we started with the sort of simplest, most basic case where we have a cart with a mass m attached to a spring with a spring constant k. And we got a differential equation of the form x double dot plus k over m times x is equal to 0. And the solution was a function x of t that's equal to a times the sine of the quantity square root of k over m times t plus phi. Where a is the amplitude, square root of k over m is the natural frequency. It's not a real frequency, but that's what it's called. And phi is called the phase angle. And I was going to say something else. So the period then was 2 pi times square root of m over k. And you can see from that that the time for one oscillation increases if you increase the mass, decreases if you increase the spring constant, make the spring stiffer. And because of that, the frequency, which is always just 1 over the period, is 1 over 2 pi times the square root of k over m. Okay, so that's what we got last time. In general, so for general free oscillations, that's unforced, the differential equation is going to be x double dot, whatever that x here is sort of standing in as a general variable, because we'll have ones that deal with rotations and stuff too, plus omega n squared times x is equal to 0, where omega sub n is the natural frequency. And the solution has the form x of t is equal to the amplitude times the sine of the quantity omega n t plus phi. By the way, something to pay attention to, especially because we're going to be using this pretty much the exact same equation in D form for column buckling. In this class, we had the equation, x double dot plus omega sub n squared times x is equal to 0. and use the general solution x of t is equal to a sine quantity omega sub nt plus phi. But that's equivalent to another form of the general solution. And this totally equivalent, just sort of rewording of this general solution is the one that we're going to use for column buckling. So column buckling in D form. And that form is that x is equal to C1 times the sine of omega n t plus C2 times the cosine of omega n t. Those mean totally the same thing. There's a defined relationship between A and C. You could go one way or the other way. It just sort of has to do with which form is kind of, helps you visualize what's happening better. And there's also a solution. This equation is the solution for how'd that problem go in tutoring the other day? Did you guys get through that? No, you didn't. I didn't either. Oh yeah. I don't know. Yeah. Well, anyways, so I was tutoring physics 2, and someone came in with a problem that had an inductor and a capacitor, and in a circuit like that with an inductor and a capacitor and a starting voltage, you end up with an equation just like this too, and the current oscillates back and forth, and so you can use this same solution approach for something like that in theory. I wasn't able to do it, and apparently Tim wasn't able to do it either, but that solution is there. Okay. So now I want to talk about so this is what I want to talk about today. What changes when the spring, the spring mass system is arranged vertically. The answer is not much. I'm going to go through a derivation of that, and I'm going to ask you to go through similar derivations, so you need to sort of follow the steps on this. But the answer is not much. The frequency doesn't change, so the period doesn't change. The only thing that changes is the center point of the oscillation goes from being the resting length of the spring to the spring's length when the thing's hanging in equilibrium. Then I want to talk about when you have springs in series and parallel. How do you deal with those? And I'm going to go through like a derivation of of how that works out. Then I want to talk about torsion springs. And pendulums. And those, then we will have covered all the main simple ways that these oscillations go. And then from there, we'll go into combining these different things to different 1 degree of freedom systems of oscillation. Okay, so first, I want to do a derivation of the equation and solution for a spring mass system hanging vertically. So the difference now is that we have to deal with gravity. In the example we did last time, there was a weight force down, a normal force up, but that was out of the totally out of the direction that this oscillation was happening, and so they just sort of disappeared. Now that stuff is going to be involved, and so now we have to make a distinction between the object's location and the spring's resting length and the object's location when the system is in equilibrium. We're going to choose, we're going to set our x equals 0 at the object's location in equilibrium. Okay, so no, equilibrium is if it's just hanging there and you don't have any acceleration, the object's position. And so the springs, what I'm calling the spring's resting length is so this is the length that the spring would have if it was just sitting on a table. You know? And then you hang it from here, put a mass on it, and the mass pulls it down a little bit. You know, and so this is right. So this is the rest length. This is the equilibrium length. And this is what we're going to call, you know, that's like our origin, and our x is going to go towards the ceiling. And so the rest length of the spring, let's see, when the spring is at its rest length, that means it applies zero force to the mass. The object is at location x0. And notice that that x sub 0 is positive. Okay, so what's going on now is that in this system, because the spring and gravity don't interact, when this is at equilibrium, the position it can just sit at, the spring isn't producing any force. When it's hanging, when it's at equilibrium, that spring is producing force. And so the magnitude of the spring force so the magnitude of the spring force isn't kx anymore. What is it? There's a k. Kx minus x naught. Yep. And we have to deal with the signs or whatever. That's not really I don't know. That's not really always a magnitude necessarily, but the absolute value of that is the magnitude, and we have to think about the directions. Well, we're going to think of x as being, so it is a position. So x could be negative down here, positive up there, and then I guess just think of that as absolute value, but we're not technically. We're just using x only. You could use y instead. All of the equations I'm using are in terms of x, so I'm going to keep it that way. All right, so now let's draw a free body diagram. And before we go into the one for the oscillatory motion, let's do a free body diagram and Newton's laws for the thing in equilibrium. So there's the mass. We have the weight acting down. And the force of the spring, I'm going to draw it up, and then if it's, if you have a positive, let's see, so if x minus x sub 0 is positive, the spring's going to be pushing down. So this is going to be negative k times x minus x 0. And we've chosen our x equals 0 to be at the equilibrium position. So this goes away. Okay, and x naught is at the spring's resting length, but we chose x equals 0 to be at the equilibrium length. Okay. Yeah, I know this is yes, it is awesome because if you don't do it this way, you can't calculate stuff. And so Newton's second law, just in the x direction, says negative, negative. So k x0 minus mg is equal to 0. Yeah. So k x0 is equal to mg. This will come up. Well, this will come up in the rest of our derivation. We're going to use this fact in the next part. So now finally we can do the free body diagram and Newton's second law in a general case. So this is the one that's going to relate to the oscillation. Here, we have the weight acting down. We have the spring force, but x is not necessarily equal to 0. So this is negative k times the quantity x minus x0. Is it clear to everybody what I'm doing with that sign there? So the way I think about these signs is I know that it's going to be plus or minus k times the distance from the current position to the resting length of the spring. And then I just think about if that value here is positive, what's the direction of that force? So if this is bigger than that, we're this way from the resting length of the spring. If we move this way, the spring is going to be pushing down, and that's why I gave it the negative. I don't know. There might be simpler ways to do it, but that's the way I do it. So what it does is it says if this is positive, the spring is going to be pushing down on that. If the spring's pulling up on it like that, this has to be negative, meaning you have to be stretching the spring. Because, if you stretch a spring, it pulls on it. If you compress a spring, it pushes on it. So that's just the way that I think about that. And now Newton's second law. X component only. Says k negative k times the quantity x minus x sub 0 minus mg is equal to ma. And if I move stuff around, I get that ma plus kx minus kx0 is equal to negative mg. So let's make sure all my signs are right on that. So I sort of switched the sides here, but I kept the mg on that side. I moved this stuff over there, and so I think that's right. And now acceleration is x double dot So we have x double dot plus kx, and then kx0, this is where I'm going to use this fact, what we know about equilibrium. This is equal to negative mg, and all that's equal to negative mg. And so these two things cancel out. And we end up with the equation that says x double dot plus k over mx is equal to 0. Okay. So even though, well, so what's the same and what's different? Obviously, the form is the same. What's different? No, that's the same. That's the same, wherever it is. The only thing that's different is our x equals 0 stands for a different position. So x equals 0 at the hanging equilibrium position. Not at the spring's resting length. Okay, so the oscillations are going to happen around that equilibrium position, not around the resting length of the spring. And you know, I think just intuitively it's a little surprising that it works out the same. I mean, this says that the solution has to be the same. So x as a function of time is equal to a times the sine of the quantity square root of k over m times t plus phi. And all of those mean the same thing they did before. And so the period is equal to 2 pi times square root of m over k. And so the frequency is equal to 1 over 2 pi times square root of k over m. Yeah, well, yeah, there's a few things that are sort of intuitively surprising about this, I think. But why doesn't it? I mean, I guess I don't mean this as like a smart-ass kind of answer, but really the answer is this derivation, you know, like we just went through the physics of it and that's how it works. And I don't really have a better answer than that. I mean, my intuition also sort of says like, well, when the weight pulls it down to that new position, wouldn't that sort of have the effect of making it a stiffer spring or whatever? Like I would think maybe the oscillations would be a little faster or something, but I don't know. It doesn't happen, and that derivation tells us that, you know. So let's do an example. This will also be an example of how to use the boundary conditions to find those constants. So let's say that we have a spring stiffness of 500 newtons per meter and a mass of 0.2 kilograms. And from the hanging equilibrium position, let's say that we pull the mass 1 centimeter down and release it. And we want to find the differential equation that defines this motion. And we want to find the solution x of t. And then let's say we also want to find the frequency. That's actually probably easier than the other stuff. So the way we're going to do this is draw a free body diagram. We have negative 500 times let's not do all this. Sorry about that. I will have you do a couple of questions where you do derivations of stuff, but let's just go straight to the differential equation. So we know that the differential equation is x double dot plus k over m times x is equal to 0, where x equals 0 is at the equilibrium position. And so we have x double dot plus k over m 500 over 0.02 2500. Right. So 2500 x is equal to 0. And so the general solution is equal to a times the sine of the square root of 2500 times t plus phi. That's not really an explicit solution yet because we don't know what a is and we don't know what phi is. So now we're going to use the boundary conditions to find a and phi. What's the square root of 2500? Ooh. Yeah. A sine quantity 50t plus phi. All right, well, we know that at time equals 0, x is equal to, what's x equal to? If we, yeah, and remember that we're doing this all with positive x going up, and we pulled it down. So x is equal to negative 0.01. And we're releasing it from rest. So also at time equals 0, x dot is equal to 0. So I'm going to use the x dot condition first because the zeros are easiest to deal with. So x dot as a function of time is equal to 50a times the cosine of the quantity 50t plus phi. And so when time is equal to 0, we have 50a times the cosine of phi is equal to 0. So that's our first equation. And then our second equation says, x as a function of time is equal to a times the sine of 50t plus phi. We know that this is equal to negative 0.01 at time 0. So a times the sine of phi is equal to negative 0.01. And there are multiple solutions of this. We don't want that a to be equal to 0, so we're going to look for solutions where, okay, so this is our second equation. We don't want our a to be equal to 0, because that would just give us 0 for the solution. So we're going to say that equation 1 is only going to be satisfied when cosine of phi is equal to 0. And when does that happen? Yeah, pi over 2, negative pi over 2. Let's just use those two. And equation 2 then, I'm going to choose this one so that, because it's going to give us a positive amplitude, but there's no reason to choose one over the other one really. Equation 2 says a times the sine of negative pi over 2 is equal to negative 0.01. So that says negative a is equal to negative 0.01. So a is equal to 0. Yeah, I'm not done writing yet. 0.01.
That's what I lost your exam.
Yeah, exactly. Okay, so what we have is that the solution, x of t, is equal to, yes? Yeah, you could, since A is the first letter in amplitude, I chose the one that I knew was going to give us a positive value of A. But this would be perfectly valid if you did this as, so I'm going to write this as 0.01 times the sine of the quantity square root of k over m times t minus pi over 2. And that's exactly the same function as negative 0.01 times the sine of the quantity square root of k over m times t plus pi over 2. So whichever one of those two you chose, you get one of those two forms.
I'm going to try to pull that on an exam. I wasn't done reading.
Okay, and then, so what's the natural frequency? And this is equal to 0.01 times the sine of the quantity 50t minus pi over 2. Or negative 0.01 times the sine of the quantity 50t plus pi over 2. So from this, the natural frequency is equal to 50. And what are the units? We're going to multiply it by, well, we know that what's inside the sine has to be units of radians. We're going to multiply it by seconds. So this is in units of radians per second. Or 1 over seconds. And so the frequency is equal to 1 over 2 pi times the natural frequency, which is 50 over 2 pi. And what's that as a number? What? 25 over pi. 7.958. And that's units of 1 over seconds or hertz. 1 over seconds is equal to hertz. Any questions about that? All right, well, let's stop there. And next time,
What's going to be in our exam on Monday?
good question. So next time we'll do series and parallel springs. Pendulum. Oh, and before that, I think I said torsion springs. A reverse pendulum. Sure, we can do that. Okay, so exam 4 is on Monday. The topics, let's do everything up through rotating coordinate systems. Yes, we didn't do any rigid body stuff in rotating coordinate systems. Any questions about the test? Well, I mean, everything up through there is fair game, but I guess it'll be weighted more heavily than other topics. I think next Friday, okay. So yeah, right. And then the final, but then we're done. Yeah. So yeah, don't focus on the Negative. Think of all the freedom that's coming after all this stuff.
The freedom to follow and soft and sorrow.
Yeah. It's about a month right now, I think. Yeah.